I've got a problem involving radioactive decay for you to try. I took this from question number 28 in your text, although I modified the directions just a little bit. Okay. Just a reminder up here of the general form for radioactive decay. This problem involves strontium-89. A patient would be given 4 millicuries, and we're told that 20% of that remains after 90 days. Okay. So the first thing I'm asking you to do is write a function of this form. Same thing I've got written up here. Use the general model for radioactive decay to model the amount of strontium-89 in the patient. And T would be the number of days from the initial injection. I know to use units of days just because that's how my data was given to me. Okay. And I'm asking you here, don't round to find your value of K. Give it exactly, so you'll be expressing it in terms of a natural log. And then, once you've got that, use your model to find the half-life. Find it both exactly and round it to the nearest day. Now, the half-life is a length of time, so you're going to be solving for a time. It's the amount of time it takes for half of the stuff to decay. So, if we started with 4 millicuries, the half-life would be the time it would take for that to decay down to 2 millicuries. Okay, so pause the video, give that a shot, and then we'll take a look together. As with the last example, Q naught we were given exactly. Q naught is just 4. That's the amount of the initial injection. So my model is Q is equal to 4 e to the negative kt. Okay. Now, we're told 20% of the stuff remains after 90 days. So that's when T is 90, our quantity is 20% of that initial 4. Now, I could multiply that out, certainly. That's just going to give me 0.08. But I'm going to actually write that as 0.20 times 4 equals 4 e to the negative 90 times k, just plugging in 90 for t. The reason I'm choosing to write it that way is because I know I'm going to want to isolate this exponential expression so that I'm going to want to divide by 4. And when I do that, I'm left with that 0.20 corresponding to that 20%. So it's always going to be that the ratio that I get when I isolate the exponential expression, what's on the left is the ratio of the quantity I have at that time divided by the initial quantity. Okay, so let's see, 0.20 is equal to e to the negative 90k. So then I can take the natural log of both sides. Natural log of 0.20 is equal to negative 90k. So k would simply be negative natural log of 0.20, or 0.2 would be fine to write, over 90. Okay. So that's my exact value for k. So my model is Q is equal to 4 times e to the negative ln of 0.2 over 90 times t. Okay. So the negative there. This negative, again, natural log of 0.2 would be a negative number. Okay. So we're taking the opposite of that so that this number that I have in parentheses here is actually positive. Okay. So that's my answer to the first part. That's our model. I want to now find the half-life. Well, as I said, if I started with 4, the half-life is going to be the time at which that's decayed down to 2. So 2 would equal 4 e to the, now I'm going to go ahead and simplify, natural log of 0.2 over 90 times t. I'm going to just cancel those two negatives. Dividing by 4, notice I get 2/4, which is 1/2 or 0.5. Again, when you isolate the exponential expression, what you'll have on the right is the fraction, the ratio of the quantity you have at that time divided by what you started with. At the time of the half-life, that fraction is 1/2 or 0.5. All right, I'm going to just rewrite this a little bit. Actually, never mind, I'm not. I'm going to leave it like so. E to the natural log of 0.2 over 90 times t. I was initially thinking I might change the base and take advantage of the fact that these guys cancel, except I want to bring that exponent down, so I want to take the log, and I'd prefer to have the base of e when I take the log. So natural log of 0.5 is equal to the natural log of e to the natural log of 0.2 over 90 times t. The natural log undoes the exponential function, so the natural log of 0.5 is equal to the natural log of 0.2 divided by 90 times t. I want to solve for t, so I'm just going to multiply both sides by the reciprocal. So 90 natural log of 0.5 over the natural log of 0.2 is going to equal t. Multiply by 90, divide by the natural log of 0.2. So that's my half-life, because that was the time at which we would have half of this stuff left. So that's what we were asked to find in the second question. And then, just because I'm curious, and because I said we should be curious, let's plug that into a calculator and see what that gives us to the nearest day. So 90 times the natural log of 0.5 divided by the natural log of 0.2. And I'm getting 38.76 blah, blah, blah. That would be about 39 days. And that makes some sense. We had 20% of the stuff left after 90 days, so I knew the half-life needed to be shorter than 90 days because we had decayed below half of the initial amount after 90 days. So our half-life here would be approximately 39 days.